Thank you again. Again, I'm a PhD candidate at Clemson University, and this is joint work that I've done with my advisors, Dr. Yangzhe Song and Dr. Scott Mason in the Department of Industrial Engineering. So I'm going to go a little bit quickly in the beginning because we're a little bit limited on time. There we go. Oops. I'm at the very end, unfortunately. Sorry about that. So we're dealing with unmanned vehicles. They're used for a range of applications, a lot of them in government and military. What we're going to focus on are just reconnaissance and surveillance missions. And again, there's a lot of advantages for utilizing unmanned vehicles for these purposes. We're dealing with just a directed network. We're dealing with a set of waypoints V, in which these set of vehicles can travel through. These waypoints are assumed to be fixed and known a priori, and we're going to route them in such a way that we cover or observe an unreachable set of targets W. Again, we're trying to accrue a level of information about these targets. How do we do this? Well, coverage is going to be accrued based upon the proximity to and the time near said targets. And I'll talk about that in just a little bit more detail coming up. One thing that with unmanned vehicles that we're going to account for is their energy supply, and we're going to approximate that by some operational deadline, and we're going to call that T. So in terms of coverage, real quick, if I have some target W and some nodes IJ, we can say that the amount of time that we're really curious about from traversing node arc IJ is what's highlighted in red here, right? It's how much is in that coverage area defined by that target. So I really need to know the length of that intersection, but also how much time I'm spending within as well. And we do that via pre-processing. We're going to set a bunch of assumptions for our problem, such as an identical set of vehicles and constant state velocities across the arcs, and a few others as well that I won't go into too much detail for. I do want to go over the formulation real quickly. The things I want to highlight are the objective function, where we're maximizing the coverage of all targets. The first term is the coverage accrued while traversing a given arc, and the secondary term is that spent idling at a given waypoint within range. Notice that we're dealing with the time aspect here. This is the time traversing arc IJ for vehicle K, and so we're really dealing with speed optimization within our problem, and we want to know what speed do I traverse arc IJ. We have some schedule feasibility, operational deadline constraints. You have your vehicle routing problem constraints as well, and then some covering torque constraints in the main formulation. The one I do want to highlight here is this last one. What this does is it enforces the sufficient coverage of each target. Again, it's identical to that of our objective function, although now we're bounding it below per target. It's also the problem constraint, if you will. It actually links the vehicle fleet itself in the formulation and makes it non-separable. And so what we're going to do is institute a Lagrangian relaxation-based approach by adding the multipliers to the coverage restrictions itself. Now we want to solve the relaxation, and things we're going to do with this is try to exploit some of these optimality structures that we can find out. And the thing I want to highlight is now in the formulation, I no longer have a requirement of coverage on a given target. And so really what I'm just trying to do is get as much coverage for the set of targets as possible, but no minimum level. And we can find something neat about where we're allocating our idling time at along the route. And so if we consider a path through the network, and I intersect two waypoints that can accrue coverage by only idling, because it's on the perimeter of their coverage areas, I want to know, where do I want to idle? Well, if this is a higher priority target, I'm going to actually idle there, and I'm going to move my allocation time to that node called V bar. And we're going to make use of this. And so really what it is that I'm going to idle at most one location, and we're going to call that V bar. Knowing V bar, I can come up with a set of paths that go through the network that are feasible, and we can do a free formulation of the Lagrangian relaxation. But again, this optimality structure is only true for the Lagrangian relaxation and not for the model itself. And so we can come up with this, define the set of paths P going through V bar for a fixed Lagrangian multiplier lambda, and we can write the formulation as follows. What you might notice out of this is that when we do this, we see a continuous knapsack problem. And what we really want to know is, well, how am I going to allocate my variables between their lower and upper bounds? And that really depends on the operational deadline T. And we'll see that in a continuous knapsack problem, things are going to go to their lower bound or upper bound. And if T is restrictive, I'm going to put 1 at a fractional value. What else do I know about the optimality structures and how I can allocate these times? Well, once I fix V bar again, everything's going to follow from this. I actually know the objective weights. I can determine if they're positive or negative or zero. If it's positive, that means it's benefiting my objective. I want to go as slow as possible. I mean, I want to set it to its most time, right? The slowest time. And if it's negative, I want to set it to its fastest time. I want to get out of that arc as fast as possible. And so what is this going to do? Well, we're going to take all possible waypoints where it's attractive to idle, call it V bar. And we're going to basically iterate over all of these to find their best paths while waiting at V bar. And then from those set of paths, choose the best one. And we're also going to include the node 0 as the idea that we don't idle at all, because I can idle at most one, but I may not have to idle. And so we can look at a labeling algorithm then to go ahead and do this. We're going to say that each label represents a partial path. We're going to store the set of waypoints that each path actually visits. We're going to account for the adjusted coverage. So that's the benefit to the objective function by traversing arc ij, knowing that I'm going to idle at some point V bar. And we're going to keep track of the summation of those adjusted coverages of the arcs in that path and call that the cumulative adjusted coverage. And we're going to perform partial enumeration of these labels via dynamic programming algorithm. And then again, we really need to pay attention to is if that operational deadline T is binding or non-binding. And so how do we determine dominance rules? Well, again, everything falls from V bar. And so if I consider two labels, L1 and L2, where L1 visits a subset of waypoints than L2 visits, L1 and L2 end at the same vertex, and L1 actually arrives earlier with greater coverage, I need to now account for V bar, right? Because that's our crucial point in our reformulation. If both labels have V bar or don't have V bar, it's a simple copy and paste idea of the extension. Any extension I apply to L2, I can apply to L1. And if L1 dominated L2 before, it will for any extension, and we can move forward. The problem comes with what if L2 has V bar, is visited V bar, but L1 has not? What that means is I can't just do a copy and paste in terms of its extension like I would want. What I really need to now do is in that label extension, I need to now insert V bar. I need to account for traveling to that node V bar and then traveling back. And that adjustment or that detour, if you will, we're going to call the extra coverage. And we really want to look over the worst case scenario. And so out of all possible extensions, I want to know what's the minimum coverage I can accrue by taking that detour. And if take that minimum value and the coverage of L1 with that min value still outdoes that of L2 for any possible extension, I can determine that L1 will continue to dominate L2. Again, taking in terms of their time restrictions as well, I want to make sure that L1 visits its set of waypoints earlier than L2 does. And so how do we do these label extensions? Well, it really comes down to the idea of the token, right? In a fractional knapsack problem, I know one's going to take a fractional value, but when we're working through this algorithm, I don't actually know the full path yet, so I can't make that determination. And so we get to two extension rules. If the adjusted coverage is negative, I'm going to get off that arc as fast as possible, and we're done. If it's positive, I would like to go take my maximum time as slow as possible, but I may not be able to do that because I may reach my operational deadline. And so I need to account for both extensions. And if I have a case in that, I'm going to call those trade-off arcs, and I'm going to store those for those extensions using their ratios. Now, if I look at a ratio and it fits above this threshold 1, right? I take a maximum value, I'm going to set it to 1. Minimum value, I'll set it to 0. And if it fits into, the ratio fits somewhere in here in the extension, I'm always going to set that to value 1. If it fits in here, I'm going to set it to value 0. And the question becomes what happens somewhere in the middle. And so these illustrations will show that idea that depending upon those max and min values. But if it's in the middle, I don't know what to do, and I have to account for both cases. And so my extension actually doubles my label set. And so I'm now blowing up that search space, if you will. And so that's how we extend it. I now want to look at the dominance for these. And so really comes to is at the end of the path, I know I can apply a token. And so if I apply a token to, say, some node, a trade-off arc that was at value 0, that means I'm going to move it from 0 towards value 1. And in doing so, increases its time and its coverage. But I could also just the same take something that was at value 1 and move it towards value 0. and I get a reverse piecewise linear function where now the time is decreasing because I'm moving it from its max value to its min value. And in doing so, the coverage will also diminish. And so we get a picture that looks like this in terms of the label value. And we want to know, does a label L1 dominate L2? Well, we get 4 cases. And I don't want to go into too much detail because of time. But in this scenario here, we see that L1 dominates all extremes of L2. And so L1 would dominate L2. And in case 2, we see that L1 dominates L2 in terms of its time, but I'm not sure about coverage if I were to apply a token. And I need to make sure that there exists a solution for L1 applying the token that will do better than the max value that L2 could. This case is the reverse side of this, and then we get the concatenation of case 2 and case 3 to get the 4th scenario. Quickly going over the solutions, we come up some stuff with Solomon instances to generate a data set. We implemented a 7,200 second time limit for all methods, and we use Cplex. And we see that the Lagrangian dual bounds are 26% tighter than the initial relaxation bounds. And the dual bounds are actually 0.2% away from Cplex's best solution. And a lot of what Cplex does, they can't finish actually in the time limit itself. We don't include any large instances because the state space actually really does blow up in those scenarios. And you may be asking, well, okay, so the Lagrangian dual bounds are better, but what happens in terms of the convergence of those bounds? And we actually see that our algorithm finds better bounds more quickly than Cplex does. And so we see really promising results for smaller instances, not so much for the large instances. We struggle with solving those, and that's something that we need to work on in the future, as well as maybe taking account these targets being non-stationary or probabilistic in some capacity. And with that, I will end.